Hello! In this video, you will learn how Spark manages its intermediate data and how can you hint Spark about your access patterns for better resiliency and performance. Recall from previous videos that RDDs are partitioned and the whole execution layer builds around the partitions. Each task processes a small number of partitions at a time, and the shuffle globally redistributes data items between the partitions when required. Obviously, Spark transfers data over the network, and the I/O unit here is not a partition but a block, that is, a fixed size chunk of data. Usually, blocks are a few megabytes in size. Now, imagine that you are working interactively with Spark. You have a shell with a Spark context, so you can create RDDs and invoke actions on them. Imagine you are willing to load a Wikipedia dump from HDFS and see how many articles there contain the word Spark. You know how to do this, right? You need to create the RDD, apply the filter transformation, and invoke the count action. Now, among those articles with the Spark word, you would like to see how many of them contain the word Hadoop and how many the word MapReduce. Well, that is exactly the same task, you might say, and so the code will look like this in the slide. While being semantically correct, this code may perform worse than you expect. The reason is that after completing the computation, Spark disposes intermediate data and thus intermediate RDDs. That means it will reload the Wikipedia dump 2 more times, incurring extra input and output operations. A better strategy would be to cache the preloaded dump in the memory and reuse it until you end your session. Spark allows you to hint which RDDs are better to be kept in memory or even on the disk. Spark does so by caching the blocks comprising your dataset. You can mark the dataset as cached by invoking a cache method on it. Actually, the cache method is just a shortcut for a more generic method called persist. This method allows you to set RDD's storage to persist across operations after the first time it is computed. This method is parameterized by a storage level, that is, a descriptor controlling the persistence behavior. Typical values for the storage level are disk only, which allows the data to be evicted to the disk, memory only, which keeps the data in the memory, and memory and disk that tries to keep the data in the memory and evict it to the disk when running out of memory. The cache method is just a shortcut for the memory-only persistence. Also, you may increase the replication factor to make more data replicas, thus reducing the impact of machine failures. This was the tunable knob that I mentioned in the resiliency video. So, when and how should you tune the persistence level? The proof of the pudding is in the eating, so please benchmark your application to figure it out. However, here are a few rules of thumb that usually work. When running an interactive shell, it is a good idea to cache your dataset after you've done all the necessary preprocessing. That way, by keeping your working set in the memory, you would get a more responsive experience. When running a batch computation, it is a good idea to cache dictionaries that you join with your data. Joined dictionaries are often reshuffled, so it would be helpful to speed up their read times. When running an iterative computation, again, it is a good idea to cache static data like dictionaries or input datasets to avoid reloading the data from the ground up on every iteration. The static data tends to get evicted due to the memory pressure from the intermediate data. Okay, let's summarize what you have learned in this video. Sometimes application performance could be improved by persisting data across multiple operations. You can control the persistence of a dataset by choosing whether to store it on the disk or in the memory, and set the number of replicas. Best results are achieved by persisting hot, reused, static datasets in your application. That's it for this video. Take care and see you later.